Hi friends, welcome back. In today's lecture, we'll see how a diesel cycle works and how this efficiency equation can be derived in this present video. I have a question to all of you. In the comments, you just write to me, what does SI engine stands for? What do you mean by SI engine? Okay, and where this engine is actually working. If you just have an answer, you just write to me. Yeah, now the topic for today is diesel cycle. Okay, diesel cycle. I'd like to show you diesel cycle on PV and TS diagram. What does it mean? It is PV diagram, pressure volume diagram, and how the diesel cycle can be represented. You have an isentropy compression process. We have a compression process which is isentropic. I'm representing by an arrow. Then constant pressure heat addition. It's a constant pressure process, heat addition, and isentropic expansion, and constant volume heat rejection. So if I number it, 1, 2 is isentropic compression, 2 to 3 is constant pressure heat addition. It is Q added or addition, and 3 to 4 is another isentropic process which is isentropic expansion, and 4 to 1 is constant volume heat rejection. This is how a diesel cycle can be represented on a PV diagram. If the same cycle need to be represented on TS diagram, I'll show you there. Consider this to be temperature, entropy. Same. Isentropic compression comes like that because it is constant entropy process 1 to 2. Then you have constant pressure process with a slope different to compared to the constant volume process. Constant pressure process will have a different slope on TS diagram compared to constant volume process. Okay, this is isentropic compression. 2 to 3 is constant pressure process. This is pressure is constant there. And 3 to 4 is another isentropic expansion process, and this is 4, and 4 to 1 is again constant volume process. So they have different slopes, and these two are isentropic processes. Okay, this is entropy constant. Here also entropy constant. This is how generally the diesel cycle is represented on PV and TS diagrams. Now let us find out the efficiency of diesel cycle. What is the general formula for efficiency of a cycle? It is efficiency is represented by eta. Okay. Thermal efficiency is heat supplied minus heat rejected. This is heat supplied, okay? You can write it as heat supplied minus heat rejected by heat supplied. So what is heat supplied? Heat supplied is at constant pressure. So Cp times temperature difference, T3 minus T2. And what is heat rejection? There it is constant volume process, Cv. I mean coefficient, this is specific at constant pressure, this is specific at constant volume, times temperature difference, T4 minus T1. Isn't it? That divided by Cp times T3 minus T2. Let me simplify this. Here, I'll take that equation there for you. Now that equation can be simplified as 1 minus T4 minus T1 by Cp by Cv. I write gamma there times T3 minus T2. Hope you understand this. This is thermal efficiency. How? Cp times T3 minus T2 divided by Cp times T3 minus T2 is 1 minus Cp by Cv is Cp by Cv down there. T4 minus T1 by Cp by Cv is gamma that I wrote there times T3 minus T2. This is generally formula represented in terms of temperature. Now we have certain formality. We cannot leave the formula there. We have to further simplify in terms of compression ratios, expansion ratios, or cutoff ratios. There are two such ratios in thermodynamic cycle, which we, in this particular cycle, which we call as, one is compression ratio. Compression ratio is represented by R, is a general notation, is nothing but V1 by V2. V1 by V2. There is another ratio which we call as cutoff ratio. If you see there, this is volume 3 and this is volume 2. So the ratio is known as, in diesel cycle, the two important ratios you must always remember is compression ratio and cutoff ratio. Cutoff, I will talk about cutoff in some other video, but let's see what cutoff is represented. RC, I'll put it as V3 by V2. These are the two very important ratios you must remember to understand diesel cycle. Now, taking these two ratios into consideration, let us solve this equation and simplify it further. How do we simplify it further? Yeah, if you see, the efficiency equation is nothing but 1 minus T4 minus T1 by gamma times T3 minus T2. Let's say, what do we do here is, I will take 1 minus T1 out from that, is T4 by T1 minus 1 by gamma times T2 I take out, then T3 by T2 minus 1. Let's say we have this equation, okay, after taking certain things out. Now what do we have? We try to find what is this temperature ratio in terms of compression ratio and cutoff ratio. How do we do that? We have PV diagram and TS diagram. If you consider PV diagram, we have a constant pressure process, right? We have a constant pressure process between 2 and 3, right? Between 2 and 3. Let's say you apply constant pressure process there, then equation is between 2 and 3, V2 by T2 is equal to V3 by T3. When pressure is constant, during constant pressure process, that is process 2 to 3. So then this is one relation. From there you try to obtain T3 by T2 with which is V3 by V2, and V3 by V2, you know that it is RC, which is cutoff ratio, right? This is one equation. Now you take isentropic compression and expansion. Then what do we have? Process 1 to 2 and 3 to 4 are isentropic processes, isentropics, right? So if you have an isentropic process, then we can find something like between 3, 4, T4 is equal to T3 times V3 by V4 power gamma minus 1. This is one relation. If you apply isentropic relation between 3 and 4 of the cycle, diesel cycle, this is going to be the relation. Similarly, if I apply between 1 and 2, I can write T1 is T2 times V2 by V1 to the power gamma minus 1. Then let's say divide one over there. Then let's say I call this as equation 1, equation 2 and equation 3. Then if I find 2 by 3, equation 2 divided by equation 3, what do we have? T4 by T3 equals, T4 by T1, isn't it? It is T1 equals T3 by T3 times V3 by V4 to the power gamma minus 1 divided by T2 times V2 by V1 to the power gamma minus 1, right? Then you just see, it is constant pressure heat addition, constant volume heat rejection. When constant volume heat rejection in the cycle, in the PV diagram, if you see, V4 and V1 will be the same. So if V4 and V1 are the same, then what do we have here? It is T3 by T2 times V3 by V2. That's it. V4 and V1 will be the same. V3 by V2 is nothing but RC to the power gamma minus 1. Agreed? So this these two relations, like you can make use of to further simplify this, right? What I can write that. And what is 1 and 2 equation between 1 and 2 isentropic compression? T2 by T1 by T2, let's say, is nothing but V2 by V1 power gamma minus 1. So what is V2 by V1 is 1 by R to the power gamma minus 1. These are the relations. Just keep that in mind and just find out and substitute there. 1 minus T1, T4 minus T1, what I can write is nothing but T3 by T2, right, times RC to the power gamma minus 1 divided by T2 times T3 by T2. This is T2, right? T3 by T2 minus 1. Yeah. So what else? How further we can reduce this equation? If you look at the terms that we have already used carefully, there is something like T3 by T2. What is that? T3 by T2 is nothing but V3 by V2 because it is a constant pressure process, which is nothing but RC, that is cutoff ratio. What I will do is, like it is same like 1 minus T1 times T3 by T2 is RC again, RC times the RC to the power gamma minus 1 by, you can also do that by gamma times T2. This is RC minus 1. So this is again T1 by T2 is nothing but 1 by R to the power gamma minus 1. What I do is T1 by T2 is nothing but, this will be RC to the power gamma minus 1 multiplied by RC is going to be RC power gamma, right? Gamma minus 1 by gamma times, this is T1 by T2, so it should be 1 by R, so it comes as R power gamma minus 1 into RC minus 1. So if you rearrange this, 1 minus RC cutoff ratio to the power gamma minus 1 by R power gamma minus 1 times gamma into RC minus 1. So this is the efficiency equation of a diesel cycle in terms of compression ratio, cutoff ratio. Thank you for watching. Please subscribe my channel, and you are welcome with queries if you have any. And I'm going to discuss about more thermodynamic principles in my coming videos. Thank you.